This is a plastic tub with a sheet of aluminium in it, a block of carbon, and salt water. $10 of materials, most of which you probably already own. It produces electricity at 3 in the morning. It produces electricity in a storm, under snow, in a basement with no windows. It does not care what the weather is doing, and it never has a bad week in December. And here's the honest part stated up front, because the title makes a big claim and I'm not going to leave it hanging. This does not replace your solar panels. Not for household power, not for a workshop, not for anything with a plug on it. If you want watts, buy the panel. What it does is something a panel genuinely cannot do, which is produce a small, steady current continuously in complete darkness for as long as there is metal left in it. And there is a whole category of jobs where that matters more than raw output. There is a second honest point, and it is the one that makes everything else make sense. The energy is not coming from the water. It is coming from the aluminium, and the aluminium is being eaten. Let me explain that properly, because it changes what this thing is. Aluminium is a remarkably energetic metal. It takes an enormous amount of electricity to produce in the first place, which is why aluminium smelters are built next to hydroelectric dams. And all of that energy is still sitting in the metal. Put aluminium in a conductive solution alongside a material that will accept electrons, and it gives them up. Those electrons travel out through your wire, and the aluminium slowly dissolves. So the correct way to think about this is not as a battery holding a charge. It is closer to a fuel cell whose fuel happens to be a solid sheet of metal you can hold in your hand. The salt water is the road. The aluminium is the petrol, which is why the machine runs day and night and cares nothing about the sun. There is nothing to collect. The energy was put into that metal in a smelter years ago, and you are letting it back out slowly. That is worth sitting with for a moment because it reframes something you see every day. Producing aluminium from ore is one of the most electricity-intensive industrial processes in the world. Smelters are built where power is cheapest, and the industry is sometimes described as selling solidified electricity rather than metal, which means every aluminium object around you is, in a real sense, a stored energy product. The can, the foil, the window frame, the ladder. Each one holds the electricity that was poured into it during smelting. Normally, that energy is only recovered by melting the metal down and using it again, which is why aluminium recycling saves such an extraordinary share of the original energy. An aluminium air cell recovers a little of it as electricity instead, directly, which is a genuinely unusual thing to be able to do with a piece of scrap. Now, the chemistry, because there is one detail that makes this cell unusual. A conventional battery has 2 solid electrodes sealed inside it, and both are used up as it discharges. That is why a battery is heavy and why its capacity is fixed at the factory. An air cell replaces one of those electrodes with the atmosphere. At the carbon side of your cell, oxygen from the surrounding air is pulled into the reaction. You are not carrying that oxygen around. You are breathing it in continuously from the room. That is why this chemistry has such an extraordinary energy density on paper. Aluminium air sits among the highest of any battery chemistry ever measured, in the region of 8 kilowatt-hours per kilogram in theory, because half of the reactants are free and weightless. Practical cells achieve far less than that, and I will give you those numbers honestly in a moment. But the reason serious people keep returning to this chemistry is that theoretical ceiling. Now the history, and it is more recent and more dramatic than you would expect. The underlying principle goes back to Volta's original pile in 1800, which was 2 dissimilar metals separated by brine-soaked card. Every cell in this family descends from that stack. Aluminium air as a serious pursuit is a 20th century project, and it has always been driven by one number, which is a range. Military and marine applications came first. Aluminium air reserve batteries have been used in underwater vehicles and in equipment that must sit inert for long periods, and then deliver serious power on demand, since a dry cell with no electrolyte in it does not degrade on a shelf. And then, in 2013, came the demonstration that put it in the newspapers. An Israeli company called Finergy, working with the aluminium producer Alcoa, fitted an electric vehicle with an aluminium air pack and drove it roughly 1,800 kilometers on a single set of plates. Read that number again. 1,800 kilometers on aluminium and air in a car. That figure is genuinely remarkable, and it is also the reason the technology has not replaced lithium in your driveway, and understanding why is the whole point of this video. Because when that pack was finished, you could not plug it in. An aluminium air cell is a primary cell, meaning it is not electrically rechargeable in any practical way. And when the aluminium is consumed, it is gone. Recharging means physically removing the spent plates and installing fresh metal and sending the spent material back to a smelter to be reprocessed. So the vehicle demonstration was not a battery. It was a fuel tank made of metal, refueled at a service station by swapping plates. That model can work, and companies have proposed exactly it, but it requires an entire infrastructure of plate exchange and aluminium recycling that does not exist, while lithium simply requires a cable. That is the honest reason this chemistry sits in specialist applications rather than in your car. Not suppression, infrastructure. Now the second reason, and this one matters for your build, aluminium has an annoying habit. The moment it meets air or water, it forms a thin, tough layer of oxide on its surface, and that layer is an insulator. It is the reason aluminium does not rust away like iron, and it is also the reason a plain aluminium plate in salt water stops working almost immediately. The metal effectively seals itself off from the reaction. Commercial aluminium air cells solve this by alloying the aluminium with tiny amounts of other metals, typically tin, gallium, or indium, which disrupt that oxide layer and keep the surface active. You cannot easily buy that alloy, which is why a home-built cell using kitchen foil underperforms a commercial one by a wide margin, and why keeping the surface clean and abraded matters so much in a DIY build. There's a third problem called parasitic corrosion. Aluminium in salt water reacts slowly whether you are drawing current or not, which means the cell quietly consumes itself even when nothing is connected. That is why these are built as reserve cells, kept dry until needed, rather than as a battery you leave assembled. This channel exists for exactly this kind of straight answer. One honest method a week, and subscribing is how those keep arriving. Now the arithmetic, so you know exactly what you're getting. A single aluminium air cell of the kind you can build produces somewhere in the region of half a volt to a volt in a half open circuit, and delivers current in the milliamp range for a modest plate. That will comfortably light an LED. It will run a small clock. Stacked in series, several cells will drive a low power sensor or charge a capacitor. What it will not do is charge a phone at any useful rate, since a phone charger delivers 5 to 10 watts, and you are working in thousandths of a watt. Compare that to the panel in the title. A small solar panel the size of a magazine produces several watts in daylight, which is thousands of times what a home-built aluminium cell delivers. So on raw output, this is not close, and I would rather you heard that from me. But now change the question. Ask not how much, but how reliably. A solar panel produces nothing at night, nothing under snow, nothing indoors, and very little on a heavily overcast winter day. It also requires a battery to be useful after sunset, and that battery is the expensive, degrading part of any solar system. This cell produces the same modest current at midnight in January as at noon in July. It works in a cupboard. It works under a floor. It works in a sealed room with no window, and it will keep working for as long as there is metal in it, without a battery anywhere in the system. That is the genuine trade, and there is a category of jobs where it wins outright. Emergency lighting is the obvious one, and it is precisely why this chemistry is used in reserve batteries. A dry cell with the electrolyte kept separate does not degrade on a shelf, unlike every chemical battery you own. So a light built this way sits inert for years and produces light the moment you add water. That property deserves more attention than it gets, since it solves a problem nothing else does. Alkaline cells leak and ruin the torch they are sitting in. Lithium cells lose capacity and eventually refuse to charge. And the entire value of an emergency kit depends on it working on a day you cannot predict, possibly years from now. A sheet of aluminium, a bag of carbon, and a jar of salt do not have that problem at all. Stored dry in a cupboard, they are chemically inert. There is nothing to rotate, nothing to check, and no expiry date printed anywhere. So the honest recommendation is to build one now, test it, then take it apart and store the components dry with a note explaining what they are, since parts nobody can identify in 5 years are worth nothing. Remote sensors are the second. A device reporting a reading once an hour in a place nobody wants to visit is far better served by a source that produces a trickle forever than by a battery somebody has to replace. And demonstration and teaching is the third, and I do not say that dismissively. Watching an LED light up from a sheet of foil, a lump of charcoal, and a cup of salt water is one of the better introductions to electrochemistry there is, and it is genuinely satisfying. Now let me show you how to build one. The anode is aluminium, and you have several options. Kitchen foil works and is the cheapest possible start, though it is thin and is consumed quickly. A sheet of aluminium flashing or plate works far better since more thickness means more fuel. A drink can, cut open and cleaned of its plastic lining, works too. Whatever you use, abrade the surface before you start with sandpaper or a scouring pad, since you are trying to break through that oxide layer and expose fresh metal. The cathode wants to be conductive with an enormous surface area and access to air. Activated carbon is the standard answer, and a bag of activated carbon from an aquarium shop costs a few dollars. A block of charcoal works. A carbon rod salvaged from an old zinc carbon battery works. The key detail is that this electrode must be able to reach oxygen, so it should sit at the surface of the liquid, half in and half out, rather than fully submerged. Fully submerge it, and the cell weakens dramatically, because you have cut off half of your reactants. The electrolyte is salt water. Start with roughly a tablespoon of salt per cup of water and experiment upward. More salt improves conductivity to a point beyond which you gain nothing. Assembly takes minutes. Put the aluminium in the container, add the salt water, position the carbon at the surface without letting it touch the aluminium, and attach a wire to each. Measure it before you connect anything. To make it useful, wire several cells in series to add their voltages. 3 or 4 will comfortably light an LED, and with a small boost circuit costing a few dollars, you can drive something more demanding in short pulses. Keep each cell in its own container, since sharing one body of salt water lets them short through the liquid and cancels the gain. Total build cost lands between $5 and $15, and most of that is the activated carbon. If it underperforms, and most first cells do, work through 4 things in order. The aluminium may still be sealed under its oxide layer, which is by far the most common cause. Take it out, scrub it properly with a scouring pad until it is bright, and put it straight back in while the surface is fresh. The carbon may be fully submerged, which cuts off the oxygen it needs. Lift it so that a good portion sits above the waterline. The solution may be too weak. Add more salt and stir until it dissolves properly, then measure again. Or the electrodes may simply be too far apart, since every centimeter of water between them is resistance the current has to fight. Bring them closer without letting them touch. And if the cell worked well and then faded over hours, that is passivation and sludge doing exactly what I described. Lift the plate, scrub it, rinse the container, and it comes back. Now the limits, all of them. The output is small, and I have given you that arithmetic already. The aluminium is consumed, so this is a fuel-burning device with a finite supply, and when the plate is eaten, you replace it. It is not rechargeable, so do not attempt to push current back into it. Passivation is your main practical problem. That oxide layer reforms, output declines, and the fix is to lift the plate out and scrub it, which restores performance immediately. Expect to do this. Aluminium hydroxide sludge accumulates as a white gel on the bottom of the container, and it will foul the electrodes eventually, so cells need cleaning. And parasitic corrosion means an assembled cell slowly consumes itself even when idle, so store the metal dry and add water when you actually want power. The safety picture is straightforward. There is no shock risk at these voltages, no fire risk, and no toxic chemistry if you use salt water. Some published recipes call for sodium hydroxide, meaning caustic soda, because it performs considerably better than salt. I would not use it for a casual home build, since it causes serious chemical burns and is genuinely hazardous to handle. Salt water is safer and adequate. The reaction of aluminium in solution produces hydrogen gas, which is flammable, so never seal the container airtight and keep the cell away from open flame. Keep it out of the kitchen and away from food surfaces. Wash your hands and dispose of the sludge sensibly rather than pouring it down a drain repeatedly. The ledger for the whole story then. Aluminium, free from foil or scrap, or a few dollars for plate. Activated carbon, $5 to $10 for a bag that will make many cells. A container, free. Salt, negligible. A wire and an LED, a couple of dollars. A boost circuit if you want more, $5 to $10. Total, $5 to $15. For a device that produces electricity in complete darkness for as long as you feed it metal. Here's the thing worth keeping from all of it. In 2013, a car drove 1,800 kilometers on aluminium and air, which is a range no lithium pack of comparable weight has ever matched, and almost nobody has heard of it. It did not go anywhere, and the reason is not a conspiracy. It is that when the metal was spent, you could not plug it in. Lithium won because a cable is easier than a swap, and a cable is easier than building a national network of plate exchange stations. But the chemistry did not stop working. It went to the places where you cannot plug anything in at all, which is underwater, in reserve equipment that has to sit for years and then perform, and in emergency lighting that must work after a decade of being ignored. And the version you can build for $10 is the same reaction, running slowly in a tub on your workbench, producing a small light in a dark room from a sheet of foil. Everything this channel has gathered on power sources that work when the ordinary options fail, the cells, the trickles, the real numbers and the real limits, lives in one place, linked right below. And the comments are where this one earns its keep. Has anyone here built one, and what did your meter read? Tell me what aluminium you used and how you prepared the surface, because that preparation is where all the performance hides and almost nobody publishes it. As for the machine that moves water uphill forever with no fuel and no electricity, invented in 1796 and still manufactured today, that is on screen right now. Different problem, same century of neglect. Till next time.